I'm going to do that hopefully
Okay.
today.
Gotcha.
Let's see, how many of those I have so far? Two? First two? You did send me the third one, right?
Yes, they're
Yes.
all on the drive.
So we have all of them. I'm going to do that this afternoon.
And how would you find them? Are they just on YouTube?
I would put it on YouTube and send you the link.
Okay.
Either on YouTube or first maybe I put it on Google Drive and then send you the link. Either way, I'll send you the link. Yeah. No promise I'm going to do that today. So that, and also I've been asking this question in other sections. There was only one section, section 3, if I'm not mistaken. I asked how many have a copy of the book. Everybody raised their hands. How about here? Everyone has a copy, or still a few? Who doesn't? So you may ask the neighbors. It's edition 5. So that's that, okay? All right. So any other questions? All right. If not, let's begin. Okay. So what we've done, we derived the equation of motion. So if I can do a little bit of a brief summary or overview where we are, okay? We derived the equation of motion for a single degree of freedom system. Okay? Assuming that every system, any structure in the world can be modeled as a single degree of freedom system, right? We'll see it. And then we said that the whole mechanical vibration is basically, can be divided into 4 categories. Was undamped vibration of single degree of freedom system, or undamped single degree of freedom system. So it would be free vibration. Okay, so let me actually write it this way, would be better. Okay, free vibration and forced vibration. So free vibration and forced vibration of undamped and damped, undamped and damped. So basically there are 4 categories that we are going to study. In each of them, of course, get into details. For instance, what is force vibration? So for the time being, as you saw, we derived this equation and we are going to focus on that. We even solved the problem, or we derived the response of this undamped free vibration vibratory system. But the main reason we did the solution of that, and of course we didn't fully study that yet, was to introduce the most important concept, which was the natural frequency. That was the whole purpose. So the next topic, as I said, we are going to focus on, and we spend a few weeks, is how to model a system as a single degree of freedom. In other words, we are going to demonstrate that this little innocent looking model that we call that a single degree of freedom, in this case undamped, okay, is not that it is just consisting of a single lumped mass and a simple single unit of stiffness. But this is actually a model of a much more complicated system. That means this is really the equivalent of the stiffness of the entire system. What does that mean? A system, let's look at it, a building, consists of floors, columns. These columns are what resist the motion of the floors, right? They resist that. So they're the ones that represent the stiffness. But you have so many of them. What this is, or what we are trying to do by developing this model is it possible to come up with a single spring that can represent all these stiffness elements? Or in case of a mechanical system, for that matter. You may have the rotating machinery, having, say, bearings, and a lumped mass being a disc, a shaft that basically is a rotating system. Is it possible to represent the entire shaft, all these bearings, with a single stiffness element so that we can represent the system as such? Mass is obviously easier. Mass is usually more recognizable or identifiable, although can be distributed inertia, but still is much easier. So let's put it this way then. So our focus in the next 2 weeks or so would be to find this equivalent system. But before doing that, I want to put your mind at ease about one simple question that I'm sure you have raised, may not have expressed it, but you have raised, is that how in the world we write this equation and we do not consider the effect of gravitational force. If you look at this, even it is vibrating freely, right, you still have this force. Or if you consider this system, oscillating or different configuration, basically, still translational one direction, you have this mass times g, or the gravitational, or the weight of the system. Why is it that this doesn't show up in the equation of motion? I'm sure you've thought about that. Even if you haven't, that's okay. I'll give you the credit. Okay. So let me put it this way. We will demonstrate that equation of motion is based on the assumption, or derived based on the assumption, that displacement u is measured from static equilibrium. In other words, let's put it this way. Let's look at it through this simple example. Okay? You've had a spring of whatever length, stiffness. You put a mass on top of this. So this mass, due to its gravitational load, is going to cause this to go through a deformation, static deformation. We're not talking about dynamics here. We're not talking about vibration. You have a mass, you put on a spring. Obviously, the force of gravity causes this to go through some displacement. So this being what? This mass has a weight of W. W is mg, is causing this displacement. In other words, W is the force that is you're exerting on this spring. So this would be K times U sub S, right? Now what we're saying is that when you talk about vibrations, you are basically measuring this U from the static equilibrium position. After this thing has settled, is in equilibrium, that's where you measure it from. In other words, if this is, say, u prime, this is u sub s, okay? And if you derive this equation of motion with respect to static equilibrium, that doesn't show up. We'll see. Okay? Which is always the case. We always look at the vibration measured or with respect to the reference point being the static equilibrium. Okay? You're not going to, if that tree's oscillating, you have to have a reference point, right? So you assume that basically it's with respect to whatever the equilibrium position that is. So let's do that. So let's say you have a force that has caused, of course, this to take place. So if you look at this and you write the equation of motion with respect to u prime, let's set up the free body diagram. You have this force Ft, you have this mg, okay, and then of course you have this m times u prime double dot, right? And then you also have this f of k, which would be k times u prime. Okay, if you measure that with respect to here. Okay, so you can write the equation of motion. You have mu dot prime plus k u is equal to ft minus mg. That's what the equation of motion would be, right? If you measure that with respect to the original configuration of the spring. But you look at here, u is u prime plus us, where us, okay, from here, u sub s would be mg over k, okay? And u prime then is u minus u sub s. So let's substitute for u prime here so that we derive this equation in terms of u, which, as I said, with respect to static equilibrium. Maybe it's a good idea to put here, this is the static equilibrium position. Okay? So let's substitute that then. So we have m times u double prime, right? Okay? And of course, this is, I'm going to substitute for that, is mg over k. So second derivative of this with respect to time is u double dot. This doesn't have, is not a function of time, so its derivative is 0. So you only end up with this, plus k times, I substitute for that, would be u minus mg over k is equal to f of t minus mg. And you can see that then this term and this cancel out. So you will get m u double dot plus k u is equal to f of t. So if you derive the equation of motion with respect to the static equilibrium position, force of gravity doesn't show up. There are cases that, of course, it shows up, we'll see later on, have some rigid component in the system, and the system is going through some rotational motion and so on. In other words, you cannot ignore the distribution of that knot, but we'll see that. So, any questions? If not, I'm going to give you a bonus problem that I want you to do as part of the first homework set, or anybody who does it, they get 5-point bonus towards your grade. So let's say you have a slope here, surface, and which makes an angle theta with horizon, and then you have something, maybe if I do it this way to let it be less confusing. You have a single degree of freedom system consisting of this mass, K, and C, subjected to a force F of T, okay? If considering this as the direction of motion, okay? I want you to show that equation of motion, okay, in x direction is independent of mg sine theta. Mg sine theta, of course, if you consider the motion in this direction, is the force that would be, if this is mg, right, which is the gravitational force, projection of that along this direction would be mg sine theta. So that is the gravitational force in this direction. But I want you to show, if you consider that equation of motion from static equilibrium, in other words, you had a spring, has already, let me give you a little bit of a hint here. So you have a spring here. This hint may be useful because I didn't get that hint in the other class, but since you're recording it, they will see it too. So you had, let's say, this spring here, right? Now, after you put the mass, obviously goes here, right? So this is now your x sub s. And now you start the motion, so mass, let's say, has gone here, okay? So with respect to here, now you're measuring that x of t. And you want to show that equation of motion. And of course, here you also have this guy as well, which is easy. That guy is a useless piece anyway. So I want you to show that. Any questions? 5 points. Okay. So with that said, as I promised, we are going to start the first part of the course. I said the course is divided into 2 pieces. I'm going to spend about 2 weeks or so on modeling. A system as a single degree of freedom system, or a structure. A mechanical system, or machine, whatever, it doesn't matter. An airplane, doesn't matter. Any system as a single degree of freedom system. So we're going to spend 2-3 weeks here. So what is the objective? The objective is, given a simple structure, we want to set up data structure as this. That means find the entire stiffness capability of the structure and identify the entire inertia that can be lumped into just one element. So we have a little single degree of freedom system that can represent the original structure. And by doing that, obviously, the whole objective is to find a natural frequency for this system. Okay? Or other things, we do the analysis of it. I would, consider 4 different approaches depending on the degree of simplicity of the structure in order to do that. So we introduce 4 approaches. The first approach is based on deriving the equation of motion using free body diagram and obviously the lumbar principle. So direct derivation, we call this direct derivation. Approach number 2 that we will be employing, if I can summarize that, would be basically using the definition or the direct definition of these terms, or the direct definition of the stiffness and direct definition of the mass in the system. Like I have summarized it here, I'm going to use the notes that I have. So in the second approach, we used the definition of the stiffness, okay, and we use the concept of superposition and equivalent systems. So that is the second approach we will be undertaking. Okay? And what I mean by equivalent systems is basically definition of the stiffness. What is a stiffness? How they are added up. The concept of springs in series or springs in parallel. All those good concepts. The third approach we use is for a more complex systems. This is good when you have a conservative system. What is a conservative system? Conservative system is what? A system that basically doesn't have that energy dissipation component, right? Conservative structures are better than conservative people. They have no bias. They're very simple, very innocent, and easy to deal with. Okay? So that's conservative system. So what we use now, if the system is more complex, we use the concept of energy methods. You've had some of that, right? The concept, the approach energy method. But as far as the energy methods is that we use, first we use the concept of course, conservative systems. That means the kinetic and potential energy, the sum is always constant. Okay? They only convert to each other, but the sum of the two is constant, right? The concept of conservation of energy. This much more complex approach is, of course, even the most complex case, And in this case, we use a generalized energy approach, which is called Rayleigh's method. Okay. Rayleigh was a British mathematician, physicist, good guy, contrary to Mr. Isaac Newton. There were a couple of really good British mathematicians, scientists. What was the movie? I forgot the name. The guy who
Imitation Game.
invented the digital computers, or fuzzy. Yeah.
That's the Imitation Game.
Yeah, the guy.
The Imitation Game is the name of the movie.
Oh, right. That's right. Yeah. What a movie. Yeah, that guy, poor guy, founded the whole field of artificial intelligence, digital computing, and then what happened to him? They killed him, right?
Well, in a sense,
They killed him.
he killed himself.
I know, but they forced him to take these drugs, right?
They drove him insane.
Yeah, he drove himself to death, but they literally killed him. And there was another good guy, right? In our time, a couple of weeks passed away, Stephen
Hawking.
Yeah, what a guy. Amazing. Yeah, the second Einstein. But anyway, I had the pleasure of actually meeting him once in Cambridge.
Oh, wow.
Yeah, attending his lecture. Yeah, it was a life experience. But anyway, so these are the approaches we're going to undertake. So let's start. So we will start with case 1, and that is deriving the equation of motion. Okay. Deriving the equation of motion for simple system. But let me say this, that all of these approaches require a very basic and fundamental understanding of the concept of stiffness, which you've all had that. You may not remember, I'm sure you had it in strength of material or stress analysis. Okay. What is a stiffness? Can anybody tell me what is a stiffness? When you say you have a structure subjected to load and it resists deformation, right? So what is the stiffness?
The resistance to deformation.
It is that. It is the ability of the structure to resist the deformation. But physically, I mean, in simple terms, how do you describe that, right? Consider you have a one-directional motion, right? You have a system, so one-directional motion, like a spring, is what? K times X, right? So when force is exerted on a system, results in some displacement, right? How about if this displacement is 1? In other words, the force that you apply is such that generates a unit displacement. So this deformability action, or the ability of the structure to resist force, is equal to the applied load. So in other words, in order to find the stiffness in a system, all you have to do, just apply a load, right? Find the displacement as a function of whatever parameters that you have, and in that expression, if you set the total deformation as 1, the force becomes equal to that. Let me show you an example instead of talking about it in abstract. Let's say you had a beam in strength of material, you had that, right? When you apply a load to this load moves this system, being a beam, in the direction that this load is applied. So in other words, this beam is acting like a spring. It's just resisting the deflection in the direction that the force is a displacement here, right? And if you have all the geometric and material properties of this beam, right, you can write that displacement is PL cubed over 3EI. So if I ask you, what is the stiffness equivalent? Or in other words, can you replace this beam with a single spring? You can. Because what this beam does is acting like a spring, resisting a deflection or resisting the displacement in the direction of the applied load. So in other words, this is what you have. This is what you have, or it doesn't matter, whatever way you look at it. This is it. So how do I find this? If you put this equal to 1, the force that results in unit displacement becomes the stiffness. So the stiffness then, in this case, is 3EI over L cubed. So in other words, you can replace this beam with a single spring. This is 3EI over L cubed. So what we have done, of course, this is a simple case, to show you that we can replace a structure with an equivalent system. In this case, the equivalent stiffness, which is all this structure does, right? So you get the point what we mean by equivalence, or what we are trying to find. We are trying to replace the physical structure by finding how to represent that with just this little stiffness and the mass. Mass, as you will see, is a lot easier. Okay, so let's just start with some examples. Okay, let's say, as an example, you have a shaft with a disc. It is subjected to a time-dependent torque. This shaft has the geometric properties of L is length, shear modulus, G, and moment of inertia of the cross-section, J. And this is just a lumped mass. Okay. What we want to do is to find a single degree of freedom system that represent this. In other words, we want to find this. So we want to find this, and we want to find this. Okay? And obviously, one of the objectives is to find the natural frequency of these systems. Because as you saw, when we wrote the equation of motion, natural frequency plays a major role in that equation of motion. Okay? So let's do that. So as I said, the first approach, we just derive the equation of motion by using just free body diagram, basically dynamic equilibrium. So if you look at this little mass here, you have this force, right, or causing the rotation. What is resisting it is a torsional spring times, in other words, some resistance, which is basically this shaft that's resisting the angular deformation, K sub T times phi, okay? And the other force, so in other words, when this is going like this, right, this is a force like that, or a moment like that, and then you also have a I phi double dot, right? It's angular, motion, rotational motion. So you have the moment of inertia times the angular acceleration, and you have this angular deformation, right? So the equation of motion then, simply just from this three-body diagram would be I phi double dot plus k times phi is equal to t of t. But what is k here, k sub t? Remember the beam that I drew? Shaft is very similar. When you have a shaft subjected to some deformation, do you remember the angular displacement of the shaft? If you don't remember, always remember, I'm sure you always remember this simple little guy from strength of material. If you have a bar subjected to a load P, and this is the properties are area, cross-section of A, modulus of elasticity E, length L. You remember the deformation, right, that this will experience. Delta would be PL over AE. For shaft is analogous to a bar. Here you have an axial load stretching the bar in rectilinear direction. Here you have a torsional load or angular load deforming this bar in the same direction as the moment of the torque is applied. Deformation takes place in the same direction that this load is applied. Deformation takes place in the same direction that moment is applied. So you can establish an analogy that theta, okay, is you replace P load with the torque. Length is the same. Instead of modulus of elasticity, you have shear modulus of elasticity, and instead of N, you have the moment of inertia. Okay? So this is the angular deformation that a shaft experiences. Remember the definition of a stiffness. The stiffness is the force that causes a unit displacement. So if this is 1, this is your torsional stiffness. So torsional stiffness then is Gj over L, where J, if the diameter of this shaft is D, was pi e to the 4 over 32. Okay? So you just substitute for those in here. I is the mass moment of inertia for this lumped mass. If this was a disk at a radius r, it would be something else. Let's just assume that it's just a lumped mass. So it's I phi delta plus, I will substitute for this. KT would be Gj over L phi is equal to T. Now you establish the analogy. This is mu double dot plus Ku. So what is the equivalent mass here is I. What is the equivalent stiffness here? Gj over L. So if you want to find, for instance, the natural frequency of this, this would be Gj over L divided by I, which of course you can substitute for J, pi e4 over 32, so you have that in terms of the geometric properties of the shaft. But simple example that shows you if you can derive the equation of motion, and based on the simple definition of the stiffness, you can find the mass and the stiffness of the system. Or in other words, you've replaced this with this little innocent looking single degree of freedom system. Any questions? Yes?
What's the difference between using phi and theta?
Phi is the angular deformation, the time-dependent deformation. Theta is the static displacement. It is, the stiffness is based on the static deformation. It is a property that depends on the static deformation. That's the definition of the stiffness. Or in other words, I should have made it more explicitly clear that the stiffness is the force that can generate 1 unit of static deformation. In other words, under static load. It is the static force that causes the unit deformation. Any other questions? Yes?
How would you model the torsional case with springs? For using the
Yeah, this is it. This is it. Same thing. The purpose of modeling is to define M and K, because M and K are what comes in this expression, omega n. Where do I have it? I do, right? Omega n, which is the natural frequency, is what? K over M. And what we are trying to show here is that this K and M are not a single component or single element, but they represent a lump sum of several actions or properties within that system. And that's what we are trying to find in order to set up this equivalent system. Yes?
Could you repeat why it's theta instead of phi?
Okay, let me show you. Phi is the angular motion. Okay? So what we are trying to do is, here you have this shaft, and you want to find the stiffness of this shaft. Shaft, of course, goes through angular displacement, right? So in order to do that, you apply a static load. That may have been confusing. This is a static load, so maybe I call it T sub S, different from that, which is a time-dependent torque. Okay, and from the strength of material, you know that the deformation that this goes through, okay, in other words, if this is the original shaft, right, it goes through deformation, this would be theta, okay. Remember from the strength of material that T was Gj over, I wrote it here, or this displacement for that matter. Theta is TL over Gj. This was from this, stress. So what I'm saying is, the stiffness is the static force that causes a unit static displacement. In other words, if you put this equal to 1, this force would be the equivalent torsional stiffness.
When you solve for KT and then plug into...
Yeah, KT, right, is this. Right, that is a KT.
I think there might be a mistake because when you plug in for KT, you replace the phi with a theta.
Oh, I see. You mean here?
Oh, to the right. Or sorry, to
To
the
your
left.
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 This one?
Left.
More left.
Or the-
Wait,
And
or down.
Yeah, that
One
phi
down.
becomes
There you
a
go.
theta.
Oh, I see. Sorry.
Okay.
Okay.
Oh.
Okay, good point. Phi, theta, psi, all that. Okay. All right, any other questions? Okay, so let's do another problem. I think you have time. Yes, we can do it. It's mass here, and it is this rigid beam has a length of L, is pinned here at this point A. Somewhere along this length, you have attached a spring that has a stiffness of K, and this beam is oscillating back and forth like this, or goes through an oscillation defined by this angle theta. You want to find the equivalent system. What we mean by equivalent system is to find K and M equivalent in this system. Okay? So approach 1 again is deriving the equation of motion using the direct approach, single degree of freedom system, a direct approach by setting up the free body diagram of the system and deriving that. So as this thing is going through deformation, is going to obviously deform like this, right? So you have a force due to the spring. You have these two forces, okay? That's how it's going to, and obviously there is, of course, this is the free body diagram, equivalent free body diagram, or the dynamic equilibrium, okay? So let's just set up, right equations of equilibrium. This spring is going through a deformation. If this is, let's say this is A, okay, is experiencing a displacement, which I call that A times theta. If this is a small angle, that displacement that takes place would be A times theta. It's actually a sine theta, since theta is very, very small, sine and the angle would be equal. So let's just basically write summation of moments in this case is equal to 0, moment about A. So you can get rid of these two forces that you don't need, okay? So if you write that, you have I theta double dot plus f of k times A is equal to 0, if this is freely vibrating, okay? But what is I? I is just, we assume this is massless, it's just a rigid bar, massless. So the only inertia term would be this lumped mass, which is point mass, rotating about a point. So this would be ml squared, if that distance is L, and it's just a lumped mass. Do you remember from dynamics? Okay, and this force K is K times that displacement, A, theta times A is equal to 0. So this becomes ml squared theta double dot plus A squared K theta is equal to 0. Let's look at it. The terms of the acceleration and the displacement, which define M equivalent and K equivalent, then would be what? M equivalent then is ml squared, and K equivalent here would be A squared K. Therefore, the natural frequency of this system, which would be basically L over A, A over L, okay, times K over F. Okay. So again, what this shows is we could actually replace a physical system, being of course a very simple physical system, with just this equivalent model, which is a single degree of freedom system. That's what we've done. Yes?
Are we assuming the f of k is perpendicular to the deflection?
Yes, we're assuming that everything is a small angle, so everything is perpendicular. Thank you.